This is a solution video to question 14 of paper 2 of the TMUA 2020 exam. So in this question we're given an arithmetic sequence T and we're told that its common difference A and its first term A and its common difference is D. We're told A and D are both non-zero and we're given this property P. We're investigating this property P that's just saying, okay, for some integers, for some positive integer M, the sum of the first M terms is the same as the sum of the first two M terms. So in other words, we're saying that as you add a further M terms after the first M terms, their sum has to be zero. So the sum of the M plus 1th term to the 2mth term sum to zero. So that's the first thing we need to notice here. We're given an example here, so where we've got A to be 11 and D to be minus 2. So the sum of the first 4 terms is this, and that's the same as the sum of the first 8 terms, which is this, because the sum of the last 4 terms is 0, because they each pair up and cancel up here. Then we're investigating whether these two statements are true. So statement 1 is saying that the product of A and D being negative is sufficient for T to have property P, and the second one is just saying D being even is necessary for T to have property P. So let's now go ahead and try and solve the question. So first, let's look at the first statement. AD is negative. Well, if AD is negative, then either A is positive and D is negative, or A is negative and D is positive. So in either case, we see that D is sort of counteracting the effect of A. So if A is making the sum positive, D is sort of making the sum more and more negative. So if D is large enough, so if the absolute value of D is large enough, so much bigger than the absolute value of A, then we can sort of see that the sum of the first two terms even could just be negative, and so property P could never hold. So for example, if we take A to be minus 1 and D to be 100, and the first term is minus 1, the second term is 99, and then the sum of the first k terms is always increasing. So that means that property P can never hold. Now, if we try and think about statement 2, then we're looking at whether D is even is necessary. In the example they gave us, they told we were given an example where M was even and D was even because it was minus 2. So if we're trying to disprove statement 2, we need to find a sequence where P holds but D is odd. So it makes sense to try and think of M being odd now, because the example they gave before was when M was even, and that resulted in an even value of D. So if we're going to try M equals 3, because that's like a simple and easy number we can think about, then we know that the sum of the last 3 terms must be 0. So let's try and make that happen. So one simple sequence we could try is we could try the sequence, say, minus 1, 0, and 1. So we're just increasing by 1 to the left. So if we do that, then no matter what the numbers here are, the sum of the first 3 terms is going to be the same as the sum of the first 6 terms, because the sum of the last 3 terms is 0. So if I continue this sequence, so 2, 3, and 4, I now have an arithmetic sequence T that has property P, so P holds. So that means it's a counterexample. So that means we know that 2 doesn't hold as well. So that means the answer has to be A.